Okay. We're going to look at functions here and determine what we call the intervals of differentiability, meaning at what points in the domain of the function is your function differentiable. So consider the past video we did on non-differentiability. We say a function's differentiable on an interval if it's differentiable for every value in that interval. And this is a linear function that's defined over all real numbers. And so what we see here is a nice smooth curve to some degree. Linear functions, like all polynomials, are differentiable where they're defined. And if it's all real numbers, well, they're defined and they're smooth for all real numbers. So this is differentiable. For all real numbers. And how we describe real numbers is from negative infinity to infinity. Now, they're not asking us to prove they're differentiable, which is going to be using the definition of a derivative. At a value, let's say a, you can prove this. They're not asking for the proof. We're just doing a visual inspection of this. And that's it, a visual inspection. So, okay. Another nice polynomial, this is a quadratic, and it's defined for all real numbers. This function is smooth, which means it's differentiable. So f is differentiable for all real numbers everywhere it's defined, and it's defined everywhere, meaning all real numbers, and the interval notation for all real numbers is what you guys see here. Okay. The constant function, and this is also defined for all real numbers, they didn't restrict the domain, is really also nice and smooth as we do a visual inspection of the curve. So we say f is differentiable because it's smooth everywhere. Well, for all real numbers, everywhere it's defined. And yet again, the interval notation is from negative infinity to infinity. It's a smooth curve. Another polynomial function. Polynomials are nice functions. This polynomial function doesn't have a restricted domain. It's defined for all real numbers. And notice it is nice and smooth as well. Smooth everywhere. So your function f is differentiable for all real numbers. And we define that to be negative infinity to positive infinity. All right, just doing the visual inspection of the curve. Okay, this is not proving this, which requires using the definition. All right. The absolute value function is a classic function that, although it's defined for all real numbers, it is not smooth at the origin. What we mean by not being smooth is you have a sharp corner. And that happens at the location 0, 0. It happens when x has the value 0. So this is a picture of a function that's really smooth everywhere but 0. And that means it's not differentiable. So we'll say f is not differentiable at the location at x equals 0 only, f is not differentiable at this location because you have a corner here. That's the only location of the corner. It's differentiable everywhere else except 0. So you say, what does that look like? All real numbers again, but you throw out 0. And in terms of interval notation, that's negative infinity to 0 up to 0 to infinity. There you go. Here's another function that has a corner here. This is where it's not smooth. You have a sharp corner. And it happens here where the value of x is actually negative 2. Got a sharp corner there. It's smooth everywhere else, but except at negative 2. So we say f is not differentiable at x equals negative 2. You got to throw negative 2 out from all real numbers. So we're throwing that single value of x. And that looks like from negative infinity up to negative 2 union 2 to infinity. This is the interval notation here. So we're given interval notation where the function is differentiable. It's everywhere, but not at negative 2. Interval notation. Interval notation. Interval notation. Interval notation. Interval notation. So we're working with the interval notation here of where your function is differentiable. All right. The function absolute value of x over x, this is a classic demonstration of a function that has a jump discontinuity here. So you got a jump discontinuity. That means this function is not differentiable at the location of that jump discontinuity. That's where x equals 0. All right. F is not differentiable at the location of your jump discontinuity at x is 0. So where is it differentiable from negative infinity up to 0? Union 0 up to infinity. All right. It's not differentiable at 0 because you have a jump discontinuity. Here's another example of a function that has a jump discontinuity here. That jump discontinuity happens at the value of x is 3. It happens at 3. So this means f is not differentiable at x equals 3 because you have a jump discontinuity. I'm going to write that down here so you guys can see that. All right, so what's the interval in which it is differentiable? Well, it's differentiable everywhere else, meaning all real numbers, but you throw out positive 3, and that looks like this. Negative infinity up to 3 union 3 to infinity. Number 9, you can notice this curve here is not smooth at x is 0. This is the location 0, 0. That happens to be where x equals 0. And at this location, if we get the highlighter out around this, let me show you, this is not smooth. We're not smooth here. I'm going to write this down. Not smooth. You have a sharp what? Sharp corner. So this function f is not differentiable at x equals 0. You got to throw 0 out. So this is all real numbers, and you throw out 0. So that means it's negative infinity up to 0 union 0 to infinity. Again, we have a function with the rational exponent. This function is smooth, but there is a location here where the curve is vertical. You can say this curve is like up and down here. Well, that's going to indicate what we have, what's known as a vertical tangent. And so our functions are not differentiable at vertical tangents. So that happens at the location, it happens at the origin again, but it happens on x is 0. You got a vertical tangent here. So we can say f is not differentiable at that location. Only at that location. We have to throw it out. It's differentiable everywhere else but 0. So we're going to write this as interval notation. And that's the exercise. This is what we're looking to do for this here. Okay, they're not asking you to prove this. We proved this in class, that it's not differentiable at 0, but you can do a visual sort of inspection of the curve. And I believe that's that. Oh, no, we got more. Sorry. We see we have a vertical tangent. I'm sorry, I keep saying that. We have a vertical asymptote. Set the denominator equal to 0 and solve for x. Well, it's already solved for x. This function at x is 0 has a vertical asymptote at 0. Well, functions are not differentiable at vertical asymptote. So we say f is not differentiable at x equals 0. So it's differentiable everywhere else. We take all real numbers, we throw out 0. And so interval notation is negative infinity up to 0 union 0 up to infinity. This is the interval for which this function is differentiable. It's everywhere but 0 because it has a vertical asymptote. Number 12, another nice rational function where we have to determine where that denominator is 0, because we're going to have a vertical asymptote where x plus 3 equals 0. Solving for x means x is negative 3. So as you guys can see from the graph here, at x is negative 3, you have a vertical asymptote. So your functions are not differentiable at vertical asymptote. So we say f is not differentiable at x equals negative 3. We got to throw that out. So we throw that out from the set of all real numbers, okay? Because it's smooth everywhere else, it's nice and smooth, meaning it's differentiable. So this is going to be the interval negative infinity up to negative 3 union negative 3 up to infinity. This is the interval for which the function is, in fact, differentiable. Everywhere except at its vertical asymptote. It's a pretty nice example. Easy peasy lemon squeezy. And now it looks like we are done. So this is reviewing, what we discussed in lecture and what we proved earlier. And I hope you guys enjoyed the visual description of what's happening and the associated interval notation.